Dickwad. So, hi class, today we are going to start off on chapter 8.2, which is the projection and the Gram-Schmidt process. Again, this is getting us to start looking into really important structures and foundations for what we're going to do for the rest of the semester, this last month that we have. So what we're going to do is we're actually going to start off with an animation of sorts, not an animation, more so of an exploration of vectors. Okay, so now we're going to just kind of zoom into a graph, and we'll use a graph as a tool to help us to explore Dickwad, some of the things we want to do today. Okay, so let's assume that we start off with a vector v. Okay, so here in purple we have a vector v of some length. It's very hard to draw the tips of a vector. It's not impossible, but I didn't want to spend a lot of time on it here. So we're just going to use the closed dots here to signify the tip of our vectors. So here I have a vector v. I have it running along the x-axis. It does not have to run along the x-axis. It just makes it easier for us to understand. It could be at a diagonal or any other length. Okay. So the next thing that we want to do is we're going to draw another vector. Okay, we will call this vector u. It'll form some angle with v. Okay, and so what we're going to do now is, from looking at u and v, we are then going to drop a perpendicular down from u on to v. Okay, so if we drop a straight line from the tip of u all the way down and have it stop at our vector v, we now have a right triangle. Okay, but we're not really interested in the triangle, but we are, it is very important for us to understand that this forms a right angle here, right? So what we're going to do now, Dickwad, is we're going to have a new vector that starts at the same initial point as u and v, right, at the tail, and it is going to end at the length of where we dropped this perpendicular at. Okay, we're going to call this new vector w1, right? So I'm having it in red here to differentiate the color. So this new vector is a scalar multiple of v, right? It's not as long as v because the perpendicular we drop, it drops down somewhere on v. So it's going to be shorter than v, or perhaps v was only this long. Then w1 would be longer than v, but it's some scalar multiple of v. Okay, so the next thing that we're going to do, Dickwad, is we're going to take this side here and we are going to turn it into a brand new vector. Okay, we're going to say it starts here where w1 ends, and it is going to be as long as the perpendicular that we dropped. Okay, so we're going to call this our new vector. So now we have a w1 vector and a w2 vector. Okay, so again, notice that w1 and w2, they are all based on the relationship between u and v. So what we want to do now is we want to take this w2 vector and we want to move it over to the end so that all of our four vectors now have the same tail, right? So let's go ahead and throw this thing over and have it start at the beginning. Okay, so now we are able to decompose u as a sum of two vectors. Okay, I can say that u is the same as w1 plus w2 because of that parallelogram rule that we have for adding vectors, right? So if I were to take w1 and w2 and draw the box that they form, the parallelogram they form, the diagonal of that length is u. So what I've done here is I've basically taken u and I decompose it into two vectors, right? One of those vectors is a scalar multiple of the v that I had, and the other vector is orthogonal to that w1 vector that I had, right? So again, just to recap what we did here, I took u, I turned it into the sum of two vectors. Those two vectors are orthogonal to each other, and one of those vectors is a scalar multiple of that vector v that I was interested in. Okay, so this idea is going to really just drive this whole chapter. Not this whole chapter, well, the rest of the class really, but definitely the rest of this section, the rest of this video. and then that will also again drive the rest of the chapter. Right, so let's get back to our presentation. So back to our presentation. Let's kind of summarize what we just did. So we'll start off with an image, very similar to what we just did in our exploration. Okay, so these are three different versions of the same thing that we just looked at. So we kind of looked at it in this form, but all of these are the same. So here instead of V, we have A. So again, this is just like we had before. This is probably the easiest way to think about it. But let's say my A was shorter than where my projection drops down. Then that new vector I have, W1, it's still a scalar of A, but it just ends up being longer instead of shorter in this case. Okay. Same thing here. Let's say U is completely in the opposite direction of A. Well, then W1 is a negative scalar of A. It still has the same direction, just a different length, and in the opposite direction because it's a negative scalar of this value, right? So these are the three different possibilities for this what's called the projection theorem that we're going to go over. Okay, so let's go over this step by step, right? So we walked through the process already, and I showed you kind of step by step what's happening. So now we're going to talk about the pieces a little bit more in depth, right? So as a summary, right, if we have two vectors which we call U and V, so the U and not A here, I couldn't find one that looked, another picture of this that looked good, that was a V, but a U and a V vector that has a shared initial point which we call Q, and then we drop a perpendicular from the tip of U down to that vector V that I have, right? The next thing that I do is I make a new vector that starts at Q and ends where that perpendicular was dropped at. Okay, I call that W1, and it is a scalar multiple of that V vector that I had, right? So I can write that W1 is a K times V for some V that is inside of, oh, I'm sorry, this should be a K, for some K that is inside of R. Okay, so K is just some regular real number, so it's a scalar multiple of V, right? So now if we turn the perpendicular that we dropped here into a vector and call it W2, that's what W2 is. So remember, vectors, doesn't matter where I place them, it's all about the direction that they go and the length that they have. So if it used to be here and I just move it over, that's fine. It's the same thing, right? So we're going to call that W2. And it should be clear that W1 and W2 are perpendicular to each other. Okay, so I can say that U is W1 plus W2, right, from the parallelogram rule that we have for adding vectors. Okay, so all of these W1 and W2 give me that U. The W1 and W2 give me the U, right? So if I want to switch this around a little bit, I can solve for W2 and say that that is U minus W1, right? So I know what W1 is already. It's a scalar multiple of V. So whatever this vector is, I multiply it by some value, and that's W1. So if I want to know what W2 is, it's going to be U minus W1. Okay. And W1 and W2, they are perpendicular to each other. So that means that I can decompose U into the sum of two vectors where those two vectors are orthogonal to each other. Okay. So U is W1 plus W2, which is the same as K times V plus W2, right? So this substitution is going to come in handy a little bit later on down the road. So now we can talk about the projection theorem. We're going to use all these things to come up with some conclusions. Look at this slowly, piece by piece. Okay, so the first thing is that I need to have two vectors in Rn, so Rn component vectors. My V vector cannot be 0. So remember, the V vector is the one that's getting projected down onto. If it's the 0 vector, it's basically not there. It's a point and not an actual vector with any length. So I cannot project down onto it. Okay, so my V vector cannot be 0. I can express U in exactly one way of the form U equals W1 plus W2. So I'll go ahead and make sure I fix that in your write-up. So again, U equals W1 plus W2, right? We have it right over here. So I don't think that should be a big problem for you. Again, the write-up will have that fixed. Okay. The other things that we have is that W1 is a scalar multiple of that vector V, and W2 is orthogonal to V. It forms a right angle with V, right? So let's do a proof. Okay, this is going to be our proof for the, not for the day, but one of the proofs that we do today. So again, let's start with our assumptions. U and V are in Rn. V is non-zero, right? So that's starting with the ifs, and then we show the thens. So this stuff. So I'm starting with this. This is all the stuff that I got to prove. I got to prove that U can be decomposed so that W1 plus W2 is U, and that W1 is a scalar multiple of V, and that W2 is orthogonal to V. I'm going to show all three of these things starting with just this assumption. Okay, so again, I'm going to let U and V be n-component vectors. V is non-zero, right? So let's assume that W1 is equal to a scalar multiple of V. I'm assuming this, right? That's why I say. We will prove that this is true later on, but for right now, we're just assuming this is true so that we can kind of get ourselves started, okay? Right, so this is not part of the proof. This next line, this is just me saying, hey, this is where we're going to go. Okay, so this is us helping, this is me trying to help us stay on track. So I'm assuming that this is true, and what we need is we need to know the value of k, and we need to have a vector W2 that is perpendicular to our vector V, such that if I add W1, this thing, plus this perpendicular vector, it will add up to my original vector. That's what I need. Okay, so this is what I'm trying to go. This is where I'm trying to go with this assumption, right? So what do I need? I need this to be true. So let's assume that U is W1 plus W2. Okay, if I make that substitution right here, then I'm going to have KV plus W2 because that is what W1 has the form of, right? So now if I start to take a dot product, because remember, when I get the, well, I'm doing this because when I start to take the look at this component wise, I'm going to need some things to go to zero, right? Particularly W2 and V, right? So if this has W2 in it, then when I take this dot product, some things should fall out, right? So I have U dot V is KV plus W2 because that's what I'm saying U is. It's KV plus W2 because W1 is KV. Dot product V. So when I take the dot product and I distribute it in, I'm going to have K times V dot V, or the norm squared of V, plus W2 dot product with V. But I know that this is supposed to be 0, right? So then I get K times the norm of V squared, because remember, if I have a constant times a dot product, I just pull out the constant. The dot product of something with itself, as long as it's non-zero, is the norm squared, right? So I can assume this W2 dot product V drops off because they are supposed to be orthogonal, right? But again, this is an assumption. We will definitely be proving this later on in this proof, right? We're just kind of assuming some things to help us get started, but we will come back to show that these things are true. So what do I have? I now have that the dot product of U and V is K, that scalar multiple, times the norm squared of V. Solving for K, I just divide both sides by the norm squared, and I have the dot product of UV divided by the norm squared of V. Okay, so that is the constant. So remember, dot product is a constant, your norm is a constant, so the norm squared is also going to be a constant, right? So I have a constant over constant is a constant, K is a constant. So now that K is known, right, W1 is known because W1 is a scalar multiple of V, and that scalar multiple I have is now this dot product over the norm squared, right? So now what I need, since I know W1, I need to find W2. So I use my assumptions to find out W1. I need to find W2, and after I find W2, I also need to show that it is then orthogonal to V, right? So I know what W1 looks like. Now let's find W2. Okay, so again, if I take that relationship that I have here for u to solve for W2, it should be u minus W1, right? So I know what W1 is, so I know what u is, I know what W1 is. I'm trying to figure out what W2 is. So W2 is going to be u minus this W1 I have, which is equal to KV, which is the same as u dot product v over norm squared of v times that vector v, right? So again, I'm just making these substitutions that I have, and that's my value of W2. But I also need W2 to be orthogonal to v. So let's dot product W2 with WV and see what happens, okay? So W2 dot product v will give me the W2 and the dot product of v, right? So this thing is just W2. So now when I dot product v, the v will distribute in to this vector that I have, okay? So I have u dot product v. I will have u dot product v over norm v squared over v dot product v. And if you notice, v dot product v, that is just the norm squared of v again, okay? So then what's going to happen? Those are going to cancel, and I'm going to have u dot product v minus u dot product v, which gets me 0, which is what I wanted. I needed W2 to be orthogonal to v, so their dot product is 0, so they are in fact orthogonal, okay? Which means that I now know what W2 looks like. It looks like this. And I know what W1 looks like. It looks like just the first part, okay? So u is W1 plus W2, okay, because that's how I derived the W2 in the first place, right? Where W1 is a scalar multiple of v, it's KV, and W2 is orthogonal to v, and that's my proof, right? So let's talk about the things that we used here, right? Obviously, this W1 and W2 are important. I went through a whole sort of Desmos exploration. I put an extra picture up. We provided a proof. It's what, 17 minutes and 30 seconds, and this is all that I've talked about so far, is this projection theorem. So let's take these pieces. These pieces are going to be very, very important for us. We're going to use them again, as always, as I always say, for the rest of the semester, right? We call W1 the projection of u onto v, or the component of u onto v. And we can write this as exactly what I had here, u dot product v over norm v squared times the vector v, okay? This is the orthogonal projection of u onto v. So again, the W1, this is how I want you guys to think about it. So let's go back a little bit, okay? W1 is the projection of u onto this vector v. So imagine now, okay, imagine that I have this vector and I have this vector only, okay? So the W2 and W1 disappear. If I had a light bulb that I shined directly over u onto v, the shadow that it would cast would be the shadow of W1. The projection of u down onto v is W1. Okay, so W1 is like the shadow that u cast on that v vector. You should have seen this in calculus 3 a little bit, maybe not, definitely not this in depth, but you do talk about projections in calc 3. Generally, you talk about projections of a plane onto, or let's say a vector in R3 down onto R2, for instance. Very, very, very similar. Okay, so you can definitely think about this as so a good picture that comes with these things a lot of times is you have a plane, and then out of your plane there is a vector, and so the projection of u onto v is basically the shadow that vector projects downwards onto that plane. That's really what we're looking at here. Okay, it's the shadow that u cast over v. So we call this the orthogonal projection of u onto v because it is straight downwards. We're casting that shadow straight downwards in an orthogonal direction. Okay. We can also call this the vector component of u along v. These are analogous terms. Really just try to memorize what this means, right? So our W2 is u minus W1, or if we make that substitution for W1, it'll be u minus this thing. Okay, and this is the vector component of u orthogonal to v. So how do you remember these? Remember, I'm taking u and I'm decomposing it. So one of the components is the one that runs along v, and the other component is the one that is orthogonal to v. Remember, W2 is orthogonal to that v, and W1 runs along v. Okay, it is the projection of u onto v. It runs alongside of v. This one is orthogonal to v. The W2 was the one that was up and down. The W1 was the one that ran alongside, was a scalar multiple of v. Okay, so just remember, it's two different components of u because you're breaking u down. One of them, a scalar multiple, is parallel, runs alongside with that v vector. The other one is perpendicular to it. Okay, so let's get into some examples now that we have some terminology, some formulas, some proofs, all the good stuff that you guys love from linear algebra, right? So for this example, let's take two vectors. I'm going to write them horizontally instead of vertically for right now, just to conserve space. Again, this should never trip you off. You can always write a vector horizontally or vertically. It's equivalent. It just depends on the way you want to look at it, right? So here we have the vector u, which is 4, 0, negative 1. V is negative 2, 1, 3. And we want to find the vector component of u along v and the vector component of u orthogonal to v. Do you remember which one is which without looking at your notes? Give you 3 seconds. Take a guess. Which one's W1? Which one's W2? Alright, the vector component of u along v is W1, and the vector component of u orthogonal to v is W2. So W1, W2, along with scalar multiple, orthogonal, the right angle, W2. Okay, so let's start with the vector component of u along v, because once we find that one, we can find the other one very easily. So again, looking at our formulas, if I know this thing, that is part of the W2 formula, right? So if I find the scalar multiple of v first, it'll be a lot easier to find the W2. If I find this one first, then it's a lot more work. Oh, I guess you can still take the u and decompose it the other way around. That's fine, but it's a lot easier just to find the v first. Or, I'm sorry, the W1. So this is the orthogonal projection. So the projection onto v, right? It's the one that goes along with v, right? So the projection is, if I were to shine a light down, this would be the shadow. It runs with v in the same direction, but not as long, or maybe possibly longer. So this is the formula I have. So I just want to find this, right? I'm going to have to find the dot product, and I'm going to have to find the norm squared. Remember, this is a vector. This is a scalar times a vector. Okay, so I will get a new vector out here. It'll be some scalar multiple of v. Obviously, we just went through the proof of that, right? But this whole thing is a scalar. So u dot product v, I get a negative 8. 0 and 1 is nothing. Negative 1 and 3. So negative 8, negative 3. My dot product is negative 11. All right. Now the norm squared is just going to be me taking v and squaring each component and adding them together. Remember, it's the norm squared, so there is no square root going on. It is just the squaring of each term. So 4, 1 plus 9 will give me 14. Okay, so this k value I have will be negative 11 14ths. Okay, times that vector of v, negative 2, 1, and 3. And again, I don't want to keep it this way. We're going to distribute this through. Okay, so this is my result. Again, the only thing that cancels is this negative 2 because they're both evens. So I got 11 sevenths, negative 11 14, negative 33 14. So that's my W1, right? That is the component of u along v, or the orthogonal projection of u onto v, same thing, right? Now I need to take this and subtract it from u, and that will give me the orthogonal component of u along with v. Okay, or onto V, I should say. The component of U orthogonal to V. So U minus projection of U onto V is just this minus this new vector I have. Okay. Make some common denominators and get everything together. And you have 17 over 7, 11/14, 19/14. So this is my W1. This is my W2. Okay. So that is my component. So if I were to add these together, they would add back to my U vector. All right. So that was our first example. Okay. So now we'll go over a couple more theorems. So again, let's just start off with the if part, and then we'll end with the then. Okay. So if I have two vectors that have n components each, so each vector is an element of Rn, again, I can't have V be the 0 vector because then I can't project onto the 0 vector. Let's say that C is a scalar multiple. Okay, it's just a scalar value that is non-zero, so it's not going to make anything go to 0. Then we have a couple of properties about our projections. Okay, our projection theorem. So those properties are as follows. Okay, first is that the projection of U onto V is in the span of V. And that should make sense because this projection is a scalar multiple of V. It is something that can be made by a linear combination of V, meaning if this was twice the size of V, I can add two V's together and I will get that scalar multiple, right? So the projection of U onto V is in the span of V, which makes sense because they are parallel, right? They run parallel with each other. They are the same thing, just one is more stretched or condensed than the other. So this is in the span of that V vector, okay? B is that this W2 vector is proportional to V, but we already know that. That's the way that it was designed, right? This is the vector component of U orthogonal to V anyways. So that's a given, okay? The next part is that if U is inside of the span of V, so basically U and V, if they are parallel with each other, if they're scalar multiples of each other, then U is going to be equal to the projection of U onto V, right? So basically if U and V already run alongside each other in the same direction, me shining a perpendicular light down, that shadow is just going to be U itself because U is not offset. It's not creating an angle with V. Basically the dot product between U and V is 0, right? Or I'm sorry, it's not 0 because they're the same thing. It's basically V squared to an extent. But there's not, U is that component that is that runs along with V. Okay, sorry, got tripped up on words for a second. The last one is that the projection of U onto V is equal to the projection of U onto any scalar multiple of V. So it doesn't matter how long V is, that projection of U down onto V is always the same thing. Okay. So here goes another theorem. Okay, so let's start off with a set of vectors. If V1, V2, Vk is a set of vectors, and that set of vectors is an orthogonal basis for some subspace S of n, right? S is a subspace of Rn. And that's why the index k is not n, right? It should be less than or equal to n in this case, because it's a smaller space than n is, or equal to. Then the projection of U onto this subspace is the sum of the projection of U onto each basis vector that forms S. Okay, so again, I can project a vector onto a subspace. And the way that I project this vector onto a subspace is that I project it onto all of the vectors that forms the orthogonal basis for that subspace. Okay, now this is a very, very, very important theorem, okay, because this is going to set us up for, again, the rest of the semester. Okay, so here, I really want to make this clear, right? If I'm going to project U onto a subspace, the basis for that subspace has to be an orthogonal basis. If I have a given basis for S, I can't just project U onto that basis in any old way, right? It has to, that basis has to be an orthogonal basis. Okay, we'll talk about later. We'll talk later about how to find an orthogonal basis, right? But that is a very important concept that is very important in things like quantum mechanics and things like that, right? Okay, guys, apologies. I don't know what this sounds like on the video, but I definitely just had some issues. So hopefully I can fix this video and it doesn't turn into a huge mess, okay? But regardless, we were talking about the orthogonal basis for a subspace. Okay, so let's continue on with this theorem. If I want to project U onto a subspace of Rn, okay, then I need to project U onto each of the vectors that forms the basis, the orthogonal basis for that subspace, right? So in order to project U onto, we'll just call this whole thing V, right? Should really say S, but whatever. If I'm calling this set V, we should say, right? Then the projection of U onto this set, onto the subspace, I'm just projecting it onto each of the pieces, okay? Okay, I'll fix this notation in the write-up. So what does this look like? Well, that's going to be U dot product with V1 over the norm squared of V1 times the vector V1, plus the same thing with V2 with V3, with V4, with all the way up until the last vector that forms that orthogonal basis for the subspace, okay? So let's go ahead and do an example. Okay, so let's consider S, these two vectors, 2, -1 and 4, 3. Okay, so we are going to project this onto our vectors S. So let's just make sure that this is a subspace. Okay, so S is a subspace. Since these conditions are true, right, it's really easy to check. We can also show that really it's just these things are linearly independent, right? If I were to, I don't know, take the determinant, it would be non-zero. It's very easy to show that they're linear independent. There's also two vectors, and both vectors have two components each, so they span R2. Okay, so as I go through this problem right now, I'm looking back and I'm reflecting. It's very obvious that these two are not orthogonal to each other. So this is not an orthogonal basis for S. So apologies that this example is off, but let's just go ahead and run through it as if that was the case. So let's say that these were orthogonal. If I wanted to project U onto these basis vectors, because we don't know yet how to form an orthogonal basis yet. We're going to talk about that soon. Okay, what I would want to do is I would want to project U onto each of these and then add them together, right? So I'm just really following this formula for the first two. I'm taking U dot product with the first vector and multiplying that times the first vector. I am dot producting U with the second vector over the norm of the second vector, and then multiplying that times that second vector, and then I add these two together, and that would give me my resultant vector. Okay, so again, I've used this example maybe 5 times, and I never realized that they weren't orthogonal. Okay, so that's always just skipped over that. So apologies. I'll fix this the next time I teach linear algebra, I guess. Okay, it's too late for right now. But again, these should be orthogonal bases, and they're not. Okay, but if they were orthogonal, this is the way that would work. Very, very straightforward. You just dot product U with each of these. You take the norm squared of each of them. You're just doing the projection of U onto each and adding them together, basically. Okay, so let's start with the next theorem, which is let S be a subspace of Rn and let U be a vector in Rn. Okay. So we have that if this is true, then the projection of U onto S will be in S because we're projecting U onto that space, right? The component of U that is orthogonal to that projection is going to be orthogonal to S. That should make sense, right? And then for the next part, So that means that this is inside of the set that is orthogonal to that set S. Okay, so the orthogonal component of U, right, that's orthogonal to the projection onto S, is going to be inside of the orthogonal complement set. If U is an S, then that means that U is equal to its own projection, right? So in order for this to lie in S, it has to be a vector inside of S, right? It's equal to its own projection onto that subspace. Okay, so the projection of U onto S is independent of any orthogonal basis. Okay, so I guess that brings me full circle back to the last example, right? Oh, no, okay. Let's see here. So regardless of what the orthogonal basis is, the projection of U onto S will always look the same. Okay, so remember before we're talking about how a vector looks under different bases. No matter what the basis is, as long as it's an orthogonal basis, the projection of U onto S will always look the same, regardless of what that orthogonal basis looks like. Okay, so that example I had previous was still incorrect because that basis was not orthogonal. Okay, so that brings us to the Gram-Schmidt process. This is a very, very important process. Super important. Okay, it lets us do a lot of really cool things. In fact, the next section that we get into is all based upon the Gram-Schmidt process, and so are all of the stuff we do after that. So this is a big deal. Okay, so let's say that we wanted to build an orthogonal basis. So again, the problem I had here was that this was not orthogonal. Okay, I could still do this problem here, but in order for me to do this problem, this would need to be an orthogonal basis. So my problem was that the basis I had for the subspace was not orthogonal, right? Remember, I was ranting and raving about it. So I can build an orthogonal basis given a basis that is not orthogonal. Okay, so, and in fact, this is the exact same thing we're going to do for these vectors. This is not an orthogonal basis for this subspace. So using these vectors in the Gram-Schmidt process, I'm able to build an orthogonal basis for this subspace. Okay, and that's what we're going to do. So using the vectors that I have as a basis already, I want to create an orthogonal basis for my subspace. So I'm going to let my first vector in the orthogonal set be just the first vector from the basis I have already. Okay. The next vector in my orthogonal set, I am going to build by taking the next vector in the basis I have already and subtracting from it the projection of that vector onto S1. So now I basically have a U minus the projection of S2 onto an orthogonal vector, right? So I'm using this projection theory to build a bunch of vectors that are orthogonal to each other. Right, so this would be like W1 and this would be like W2. So now if I want to make a third vector that is orthogonal to all of the previous two, I'm going to take the third vector in my basis and I'm going to subtract from it its projection onto the subspace formed by the other two vectors. So the projection of S3 onto the first vector and S3 onto the second orthogonal vectors. All right. So this is the process that we use, and I can do this for as many vectors that I need to for whatever space Rn that I'm in. Okay, so this is the general formula for any orthogonal vector set being built by the Gram-Schmidt process. So let's do an example. So let's consider this. This should be familiar because it's the one I was crying about just a second ago. 2, -1, 4, 3. Okay. So remember, it was not orthogonal, so that example I had previous was incorrect. So what I'm going to do is let's go ahead and take these vectors and build an orthogonal basis. Okay, so S1 is just that first vector that I had, S2 is that second. So the first vector that I have will turn into the first vector in my orthogonal basis. Okay, these are not orthogonal to each other, which was the problem I had, so I'm just checking that. It's 5, not 0. They are not perpendicular to each other. They are not orthogonal. So they don't form an orthogonal basis, again, which is what the problem was, right? So in order to build an orthogonal basis, I'll take the first vector, and I'll call that v1. That'll be the first vector in my new orthogonal basis. My next vector is going to be the second vector projected onto, or I'm sorry, the orthogonal component of that projected onto that first vector in my orthogonal basis. Okay, so in order to find v2, we just follow the formula. S2 minus the projection onto the scalar multiple of v1. Okay, so I have 4 over 3 minus 5 over 5 to -1. So I get 2, 4 as my v2. Okay, so I built two vectors. These are now orthogonal to each other, which we'll check in a second. But note that this v2 is a linear combination of the basis vectors I have already. Okay, so that means that this basis spans the exact same space that this does in the exact same way, because this new vector that I have is a linear combination of the ones from the original basis. It's just now that I've combined them in a way, in a linear combination, so that they are orthogonal to each other. Okay, so I made a new vector that's a linear combination of the old two, so that that new vector is orthogonal to the first original vector that I had. Okay, so that means that this spans the exact same space that the previous one did. Okay, so my new span is exactly the same shifting of the axes and all of that, right? So the basis, the way that vectors are formed here, they both generate R2, but the way that this generates R2 is the same way that this generates R2, and that's what's important. Okay, so both of those span the same space S in the same way. And quick check that these are orthogonal. This is 4, -4, 0. So now I have built an orthogonal basis. Okay, so that's my orthogonal basis for S. And if I want to, generally what happens is we want to normalize these vectors v1 and v2, right? So what that means is if I can have a set of vectors that are linearly independent, orthogonal to each other, and normal, I call them an orthonormal basis. An orthonormal basis is extremely important for a lot of the things that we want to do in linear algebra. Okay, it forms a very solid foundation that we are then able to build off of and do lots of really cool things. So it's very important to have an orthonormal basis. Again, it makes things a lot simpler for some of the things that we need to do. It's a very solid foundation for the math that we have to build. Okay, so what does it mean to normalize a vector? Okay, well, it basically means that the norm will be equal to 1. It makes it a unit vector. Okay, so what I'm going to do here is I am going to take this vector. Okay, a vector has a length v, normal v. So if I divide the length of a vector by its original length, it now has a length of 1, right? 2 divided by 2 is 1. So whatever the length of the vector v is already, I just divide each of the components by its own length, and it will now have a new length and a length of 1. So for my first vector in my new basis, okay, 2, -1, if I want to normalize it, I will take each of its components and divide it by its length, and same thing here, I'll take each of these components and divide it by its length. So the length of v1 is √5. That should be very easy to see. Square root of 2 is 4. Square root of 1, I'm sorry, it's 2 squared is 4. -1 squared is 1. 4 plus 1 is 5. Square rooted, √5, right? Same thing here. This is 4 plus 16. 4 plus 16 is 20, so this is a mistake also. I guess I'll have to change that next time around, next time I teach this class as well. Okay, so let's continue on with this. Apologies, again, I'll fix this in the write-up, but let's assume that this was 5. We'll just continue on as if it was. If I wanted to normalize this, I would take the components of v1 and divide it by its length. So for this one, I can normalize it and it'll be correct. That is 2 over root 5 and negative 1 over root 5. If I were to check the length of this, I would have a length of 1. For v2, this should be 1 root 5 and 2 root 5 here, because the root should be 2 root 5, not 5. So again, I'll fix that in the write-up. But that's how we normalize a vector. So both of these now would have a length of 1. Again, this one I'll fix. So then that would form an orthonormal basis. So the vectors form a basis. They're linearly independent. They are orthogonal to each other, and each one has a length of 1. Alright, so what is that? Oh, I don't know what happened.